Hey guys, it's Vasya here again, and as we said in the previous video, we are going to be discussing the solution of the Quipu function in C++. So what I'm doing here is reading the input. So we have an integer t in the number of test cases, then a and b, the range, and for each test case we read another integer d. Now, we do the sieve once to generate all the prime numbers in the range from 1 to 10 to the power of 6, which is square root of maximum b, which is 10 to the power of 12. So we will be storing all the primes in the vector primes. And how we do the sieve is as follows. So we have an array of booleans called isPrime, where we will mark each number as prime or not prime. So if it's true, it's prime, and if it's false, then it's not prime. So what we do initially is here we mark all the numbers as prime, and then we iterate over all of the numbers. So from 2 to maximum n, which is 1 million. And now we need to check if the number is not prime. We need to skip it. We don't care about it if it's not prime. But if it's prime, we add it to the vector. We push it back, and also now we need to mark all of the multiples of that prime number as non-primes. So we need to iterate basically from, for example, if we take 2 as a prime, we iterate 2, 4, 6, 8, etc., and mark all those numbers as non-prime. Here there's an if condition if I times I is greater than max n. This is only for overflow purposes because I is an integer and we don't want to overflow. So basically we start with I squared and go to max n and add I as the step. So 2, 4, 6, 3, 6, 9, etc. and mark all of them as false. Now after the sieve we have the primes in the list. Values will be our compressed range of values. So because from the range from A to B can be quite large, and we want to work with values from 0 to some other index, so we'll mark them, we'll compress them basically. Let's say the range is from 10 to the power of 11 to something else. Well, 10 to the power of 11 will be 0 in our case, and the next value will be 1 in our range. So this is what we do here. We iterate over all of the values in the range and set them in our array values. So 0 will be A, 1 will be A plus 1, 2 will be A plus 2, etc. This is what we use the values array. Now we need the factors. For each of those numbers we need to find the prime factors, right? Actually, as we said in the previous video, we do not care about the actual prime numbers. We only care about the exponents, right? So factor count will tell us for each number in the range how many times each prime number occurs in the corresponding number's prime factorization. Now we call a function prime factorization, which we are about to write, which finds all of the prime factorization of all the numbers in the range from A to B. Okay, and also as you can see here, we only need to do this once. We do not need to do it for each test case because A and B are the same for each test case, only D changes. So this is why this is a small optimization. It's not big, but it's still something. I also moved, as you can see, I moved the code here for the values because they'll also not change as A and B are fixed. There's no need to keep them in the loop. Now, as discussed in the previous video, we iterate over all of the primes and try to sieve. So let's say P is our prime that we are currently working with. We need to find the smallest number which is a multiple of P in the given range, right? So how we do that is like this. A, subtract from it A modulus P, And then we need to check, because we can, this way we can go below a, and we need to check if smallest is less than a, we simply add p. So this way, after these two lines of code, the smallest will be the first multiple of p in the range a to b. Now, we check if smallest is divisible by p, which it will be, of course. Now I notice that maybe we don't even need this if here, but okay, never mind. With index, we find the actual index in the compressed value. So remember, a was 0, a plus 1 is 1, etc. So this is how we match index to the actual number in order to get to the values. So if smallest is divisible by p, we add to each prime factorization 0, meaning that there will be numbers to add. So because it's a vector, we need to first push a value, and then we will be able to increment it. Now, index is the current number in the range that we are working with, and while that number is divisible, so while values of index is divisible by p, by that prime number, we simply increment the last prime factor exponent. So last factor index is simply the index of that, the last index of that corresponding vector of the number we are currently working with. As you can see, is factor count of index.size minus 1. So this while loop will simply try to divide the current number we are working with in the range as many times as possible with p, and increment the count of its exponent. And of course, we need to do this. We need to do this for each number in the range while skipping by p. So p is our prime number, and smallest starts from the first divisor, for example, I don't know, 12, and if the step is 3, it will go plus 3, 15, plus 3, 18, plus 3, 21, etc. So this is why we added this while loop to iterate. So the first for loop iterates all primes, the while loop then iterates the range, okay? And the inner while loop tries to divide the current number in the range with the current prime number as much as possible, okay? And this for loop at the end is what we talked at the end of the previous video, that some of the numbers can be greater than 1, right? And if they are, that means they are, what remains is a prime number, so we simply add 1 to their prime factorization exponent count. So there is, like we are saying, there is one more prime number that is not accounted for yet, so we simply add it in the list. Now, we have the prime factorization. That's good. Now what we need to do is iterate over all of the range from A to B and calculate the formula for divisors, and also calculate the Quipu function. So we are iterating over all of the numbers from A to B. This is the formula we were talking about. The total number of divisors for I is what? Well, we need to iterate over i's prime factorization and multiply with exponent plus 1 for each of the factors. You see, we iterate all of the prime factor exponents. And simply multiply by factor count of I plus 1 of index I. J, sorry. Index again is the compressed value of the range. So as you can see, the range is long, right, from A to B, but the index is only from 0 to maximum 10 to the power 5. Now that we have the total number of divisors, we need to find how many times D occurs as a multiple of I. So in order not to mess up I, we create a new temporary variable and assign I to it. Okay, I call this bed primes count. While temporary is divisible by D, simply increment this count and divide temporary by D. One more last thing remains, that is to create the result, and for each number I in the range from A to B, add to the result the total number of divisors over bed primes count plus 1. That's all. Printing the result. Now we need to test our solution. I already have the input in the input text file, and as you can see, it is correct. We are going to submit the solution now. Comment the line that reads from file, run examples, passed. We're submitting the code, and voila, 100%. Well, that's all, guys. Thank you for watching, and see you next time.